So last class we have seen execution of register reference and memory reference instructions. Okay, so now let us see how input and output instructions are executed. Before going to that, how input and output configuration, uh, how input and output devices are configured. Let us see that. Okay. It is clear without input and output devices, just a computer is of no use, right? It's because human interface, human communication, communication to external devices has happened through input and output devices. Okay, and you also know that some of the examples, if I say like a keyboard or um, output devices like display devices, if you check these devices are of slow devices. The processing is very less when compared to your CPU. These are slow devices, right? See, if for example, for a keyboard, if you press any key, the processor has to read that key. Okay, how many keys you can press within a second? Hardly, maximum 10 to 20 keys. That is completely depending on the speed of the type programmer. Okay, computer program. Okay, so hardly 20 keys maybe per second. Okay, so but if you compare the speed of your processor, uh, it is very high. The clock, based on the clock, your clock may be order of megahertz. Okay, so there per second it will execute around 1 million instructions. Okay, but here per second maximum it can give you 20 characters. Okay, so there are the comparison with respect to input or output devices with respect to CPU. The comparison is I think it is clear. These are very slow devices. CPU is faster devices. Okay, and but we require input and output devices, right, for communicate with the external environment, right? uh, we will give our instructions or data which will be available in memory. Okay, so how we store those data or information or nothing but instructions in memory through with the help of some input device only, right? Without which you can't store data into memory. That may be instructions or your data. Similarly, after the computation, the results have to be displayed or transmitted to the user through some output devices. Okay, right? So input and output devices are must. Many types of devices are there. So let us talk about a simple input device like a keyboard. Okay, uh, or output device, a simple output device like printer. Let us see. These two are the terminals. See, input and output terminals. Okay, so these terminals, here the keyboard, this will send the information and printer will receive the information serially. These devices accepts sends the information serially. Okay, each quantity will be having 8 bits. Each quantity of information is of 8-bit width. Okay, and that too it is of alphanumeric code. You can send or receive alphabets or numbers. Okay, so usually it is of ASCII formats. These will be the alphanumeric codes. Okay. This serial information from which the keyboard is giving right? So as you press a key in the keyboard, it will transmitted to a register which is called input register, okay, which is of 8-bit width. Okay, this serial information is shifted into the input register which is called INPR. Okay. Similarly, the serial information for the printer is available from the register called out register, OUT. Okay, so this is out register from which the output device will receive the serial information. And input register, INPR, is the register which is holds the 8-bit alphanumeric code that has been sent by the keyboard. These two are 8 to 8-bit registers, which will be having 8-bit alphanumeric code that has to be sent to the CPU or to the printer respectively. Okay, so these two registers communicate with a communication interface serially, right, with the accumulator parallelly. Okay, so the 8 bits that are received from your keyboard serially and they are held in the input register, those are transmitted to accumulator. And we know accumulator till now that we have studied, which is of 16-bit width. Okay, 0 to 15, 16-bit width. But lower 8 bits of the accumulator is updated with the contents of input register parallelly. Okay, they communicate with the accumulator parallelly. Similarly, the lower 8 bits of the accumulator are copied onto the output register for printing or for sending to the output devices at a time parallelly. Okay, so here a serial transmission will happen between the resistors and the accumulator. The transmission is parallel. Okay, right? So this is how the input and output configuration is happened. Here, if you observe, we have two flags. Okay, so these two flags helps for the transfer of input data or to transfer the output data effectively. See, as we know, as I mentioned earlier itself, input and output devices are very slow devices. Okay, right? So input register holds a character that is sending from the keyboard, okay, to the CPU. Okay, CPU accept it via accumulator only. Accumulator is only the communication register, okay, right? So whenever you press a key, that corresponding key code will be shifted to input register via serially. It will take certain time to do so. Okay, as and when the input register is available with a new key code to be read by your CPU, as and when a new key code is available in the input register, okay, right? So after placing that new key code, and the input device will set the flag FGI, which is nothing but input flag, as 1. Okay, so input flag will be set to 1, indicating, it is just indicating to the CPU as there is a valid new key code available in the input register, or else I can say my input register is full with a valid key code, and the computer, nothing but the CPU, has to read that key code. Okay, right? After placing that key code and setting the flag by the input device, now the CPU will read this data. It is nothing but just copying the input register contents onto the lower 8 bits of the accumulator, and then it clears the flag. Okay, right? The FGI flag is cleared by the CPU, indicating that the computer has been read the character. Okay. So as and when FGI is 0, then only the keyboard is allowed to place the new key code onto the input register. Okay, if the CPU is not read this character, right? So new key code is not accepted by the input register. it is nothing but if FGI is 1, it stops overwriting with a new character by the keyboard. Am I clear? This is the usage of FGI flag. If FGI flag is 1, it indicates to the CPU that a new key code is available in the input register. So the CPU has to read that key code and it has to clear saying that now my input register, now the input register is empty. Okay. So by observing the FGI flag, now the keyboard assumes the input register is now empty, it can place the new key code. Okay. So if FGI is 1, then CPU has to perform read operation, right? That is input side. Now, if you come for output side, in output operation, the contents to be transmitted, okay, contents to be printed onto the printer or output device is available in the accumulator. Accumulator holds the data to be sent to the printer. Okay. So the lower 8 bits of the accumulator have to be placed onto the output register parallelly. Okay. So the contents are placed onto the output register parallelly and it clears the flag to 0. Both the flags are cleared 0 by the CPU. Okay. Right. Okay. Now your printer will receive the 8-bit information from output register serially and it printed onto the printer device. Okay. Right. So now it will set the FGI flag to 1. The printer, nothing but the output device, will set the flag to 1, indicating that output register is empty. Okay. The output register is empty, so your CPU can perform a write operation onto the output register. As and when FGI is FGO, which is nothing but output flag, if this is 1, it means the output register is empty. Now your CPU can write the next character to be printed or to be sent out onto the output register. So CPU will places the next character onto the output register and then it clears the FGI flag to 0. Okay. FGO flag. So if FGI flag is 1, it means the CPU has to perform a read operation with respect to the input device. And if FGO flag is 1, it indicates that CPU has to perform write operation with respect to the corresponding output device. Okay. So after reading a key code or a character or placing a character onto the output device, it will clear the flags called flag, input flag and output flag respectively. They both are cleared by the CPU as and when it completes the operation, input operation or output operation. Are they clear about the flags?
Yes, ma'am.
Okay, so flags are cleared by the CPU and these are set by the respective devices, indicating that it needs a service from the CPU. CPU service is nothing but if it is belonging to input flag, it means that it has to read a character from the input device. It's a service required by the input device reading a character. Similarly, if FGO is 1, it needs a service of CPU, which CPU has to send a character to the printer or to the output device. Okay. So the corresponding input and output instructions for transferring the data, because it need to transfer to accumulator. Similarly, output register, accumulator contents have to be transferred to output register. Okay. For checking the flag bits and control facility, the IO instructions have the opcodes which has D7. It should be the control bits D7 should be 1 and I should be 1. Okay, these are mandatory. So out of the 16-bit opcode, most significant digit is F if you group them as 4 bits together. Okay, most significant bit is F, and the remaining bits of the instruction code, they specify a particular operation. Okay, so as we see how the register operations are decoded, because out of the available 12 bits, only one particular bit is active or one, by which we can decode the specific register operation. Similarly, even here input or output instructions. Similarly, in input output instructions, so we have around 6 instructions. Out of the available 12 bits, only one particular bit will be one at any point of time, by which we can decode the instruction like either reading the input device, like nothing but input character is placed to the accumulator. This is a write operation. The output character is updated with the character from accumulator. A skip or input flag, a skip or output flag, and two other instructions related to interrupt, enable pin or enable flag. Okay, let us see one by one. Okay, so this is the common control input required D7I, and the time state is T3. All should be 1. And the instruction code, the remaining 12 bits, whichever is the bit is 1, that corresponding bit position we are taking. If this is 1, if none of the bits are 0, then the sequential counter we are clearing to 0. It will restart with time sequence 0. If B11 bit is 1, it means that the operation is input character. Okay, so it performs read operation. So the key or the character available in input register is copied onto accumulator. So accumulator is a 16-bit register, out of which only the lower 8 bits are updated with the input register. And then it will clear the flag, input flag. Input flag is cleared, indicating that now the input register is empty, so it can accept the new character. Similarly, next out instruction, for that the B10 bit should be 1. Okay. For that, the lower 8-bit contents are copied onto output register parallelly, and it will clear the FGO flag. It indicates that so your output register is full, the printer can accept the character to be placed. Okay. And next instruction, skip on input flag. It will check the flag condition, input flag condition. If it is 1, then it will skip the next instruction. So skipping next instruction is just nothing but incrementing the PC contents by 1. Okay, so that the instruction previous one more instruction can be skipped. Because if you have a series of instructions while fetching this instruction, the PC is incremented by 1 to point to this instruction. Okay, so at the execution period of this instruction, again the PC is incremented. It means this particular instruction is skipped. Okay, so likewise you can skip based on the input flag. Similarly, based on the output flag also, you can perform skip operation. Skip on output flag. If FGO is a 1, then we are skipping. And next two more instructions are, these two are branch instructions. Okay, so next is interrupt enable flag 1. Okay, so these two instructions will set or reset the interrupt enable flip-flop. IEN is nothing but interrupt enable flip-flop. This will be set or reset. Okay, so what is the need of IEN? Okay, so interrupt enable flip-flop. So let us see its need with respect to interrupt. So new concept is interrupt here. So till now, we have seen the operations with the help of input and output devices by observing the status of the flags. Okay, so FGI or FGO. Okay, either of the flag should be 1, then only CPU can perform either read operation or write operation. Okay, am I clear? Because read operation means CPU has to wait for full input register contents. Okay, so INPR is a register. It has to be filled with a character which is coming from your input device. Okay, if it is filled, then only CPU can read the character. So after filling it, the input device will set the flag which is called FGI, input flag. Okay, it will set that, and then CPU will then read INPR. Okay, so before setting FGI, CPU, if it reads INPR, it means it results a garbage input. Okay, because the INPR is a shift register, it is an input shift register. The bits are shifted to INPR serially. Okay, right? Without FGI as 1, CPU cannot perform a read operation. So CPU has to wait for FGI to perform a read operation. Okay. Similarly, write operation. The output register has to be empty. Then only the CPU can place the next character. Right. So output register, when it will be empty, after transferring all the characters or all the bits in a particular character to the output register, and printing has to happen if it is a printer. Okay. After printing that particular character, then only output register is empty, and that emptiness of this particular register is indicated to the CPU by setting the corresponding flag, which is called output flag by 1. Okay. So whenever output flag is 1, then only CPU has to perform write operation. It will write the next character onto the output register with the help of accumulator anyway. Okay. So every case, either it is input operation or the output operation, CPU has to check the flags that are called input flag, FGI, or FGO output flag. If both the flags, any one of this flag is 1, then only CPU will perform an IO activity that can be either input operation or output operation. Okay. Otherwise CPU has to wait for the readiness of the input or output device. It has to wait. Okay. See, here check this type of mechanism or the method that is used for communicating with the input or output device is called programmed IO. Okay, so this method of communicating with input or output devices is called programmed IO. It means we will write a program that will check the flag bits FGI or FGO. If FGI is equal to 1, then only perform the read operation. If FGO is equal to 1, then perform the write operation. Else, you have to be in wait state. Okay. So a program will be written for checking these flag conditions based on which it will perform the input activity or the output activity. Okay. So that is what the first IO communication method, which is programmed IO, in which the flag bits are checked every time. Okay. See, we know how many times this flag bit is checked. If you compare, let us consider your instruction cycle, which is consisting of fetch, decode, and execution. Let us suppose it is of taking 1 microsecond. Every instruction is taking 1 microsecond time for execution, and assume that your input device or output device can transfer information at a maximum of 10 characters for simplicity, 10 characters per second. So which is nothing but uh, for 1 character, every 1 character for every 1 million microsecond. Am I correct? Okay. See, if I suppose my instruction cycle duration is 1 microsecond, if I assume this, and if I assume my input device is capable of sending characters, maybe 10 characters per second. Okay. So it means one character is sent for every 0.1 second. Am I right? Which is nothing but in terms of microsecond, if I suppose 1 lakh microsecond. Am I right? One character
Yes,
for every 1 lakh microsecond. Okay. For example, we have to write two instructions, right? For input activity, you have to execute two instructions. Computer has to check the flag bit, and based on which it has to transfer the information. Okay, so checking the flag bit is one instruction, and based on which transferring the contents of input register to accumulator is another instruction. Every time it has to execute two instructions. Okay, so nothing but it means for every half of this duration. Okay, so nothing but totally 50,000 times the flag bit is checked. Okay, every time when because my loop is consisting of two instructions, the flag bit is checked by 50,000 times, because my instruction cycle, if I suppose is 1 microsecond, two instructions are there, so it will take 2 microsecond time duration. Okay, so one character we are sending at a point 1 second. So to get a true condition, we have to check 50,000 times, out of which FGI will be one for only one time. Remaining all times it is 0, because it can send only one character every time. Okay, so these many times the FGI flag bit has to be checked. We call that as a polled. Okay, so polling method. This is said to be a polling method. Whether FGI is 1 or 0, we will poll this particular bit for 1. Okay, so your CPU is wasting its main resource time, which is the execution time. CPU resource is nothing but time. Execution time is main resource that we are wasting just by checking whether the input device is ready or not. Just for the readiness of the input device, we are wasting our CPU time. Okay, so instead of, I mean, apart from doing other some important or any calculations or processing tasks, CPU is just in waiting state here for checking just the flag bit, FGI, similarly FGO. Okay, so this is what the disadvantage in the programmed IO. To avoid this, an alternative to this programmed control procedure is nothing but the interrupt method. Okay, so let the device interrupt the processor whenever it is ready. Meanwhile, the processor will be busy in its own action. Okay, right? So for to help this concept, we are using an interrupt enable flip-flop, which is called IEN. This flag bit will be set as and when either of the device, maybe FGI or FGO, is 1. The flag bit is set. This will indicate or this will generate an interrupt to the processor. Okay, so processor will receive this flag bit and respond accordingly. That is what called interrupt method. In this method, the processor won't poll or won't check the flag bit whether it is 1 or not. It won't check for the readiness of the input or output device. As and when they are ready, they will generate an interrupt to the CPU. requesting service from the CPU, either input activity or output activity. Okay, so that is explained in the flowchart. With by interrupt method, the CPU resource time we are saving. Okay, that is the biggest advantage of interrupt method. See, so normally we are using one more R bit that we call one more flag, which is OR flag. If IEN, if interrupt enable flag. See, these flag which FGI or FGO, they won't uh, generate an interrupt. The IEN bit, interrupt enable flag bit, they will cause an interrupt. This flag interrupt enable pin is responsible uh, uh, for availing for entering into interrupt cycle basically. Okay, see IEN flag bit, here we have interrupt enable flag. If this flag is 1, it indicates that any of the input or output device requests service. Okay, so this IEN will be 1, either uh, it is FGI or FGO. Any of this is 1, then IEN will be 1. If any of, and it will check accordingly. If FGI is equal to 1, then R bit will be 1, or FGO is equal to 1, then also R bit is 1. Based on this R bit, if R bit is 1, then it will enter into interrupt cycle. If R bit is 0, it will enter into normal instruction cycle. Okay, so normal instruction cycle means fetch, decode, and execution. Okay, so at the time of execution, every time the IEN flag bit, IEN flip-flop bit is checked. Okay, so while execution time, if any of the input or output device needs service, it will set the IEN bit to 1. Okay, as and when the interrupt is enabled, then it will enter into interrupt cycle by setting the R bit to 1. Okay, so this clear?
Yes, ma'am.
So here R is nothing but an interrupt flip-flop. So this is included in your computer. Whenever R is 0, it indicates that programmer he don't want any interrupt, means any input or output activity. Okay, so your control continues with your normal instruction cycle, which is nothing but fetch, decode, followed by execution. Okay, if IEN is equal to 1, if IEN is equal to 1, the control checks the flag bits. If both the flags are 0, it indicates that neither the input device or nor the output device requires the service, and it will make your R flag bit as usual as 0 and proceed the uh, uh, normal instruction cycle. Okay, so it will proceed with the normal instruction cycle in this part. If either FGI or if either FGO, if any one of these are 1, while IEN is equal to 1, excuse me. Right? Sorry. Okay, if your IEN is 1 and either of these flag bits FGI or FGO are 1, then it will set the flag flip-flop, one more flip-flop, which is R. Okay, at the end of execution phase, the R bit is checked. Okay, if it is 1, then it will enter into interrupt cycle instead of instruction cycle. Okay, so interrupt cycle, again, it is different from the instruction cycle, because in interrupt cycle you have to see, it means R is equal to 1 means one interrupt has been generated, that it is due, maybe because of FGI or it may be because of FGO. Okay, so the corresponding activity have to be done. So corresponding activity means if FGI, due to FGI it is 1, then input activity you have to do, it is nothing but read operation. If it is due to FGO, then output activity it has to do, it need to perform write operation. Okay, so for any activity, there will be a set of instructions need to be executed. Okay, right? So those set of instructions, we call them as interrupt service routine, ISR, or interrupt service procedure, anything. Okay, so this ISR, interrupt service routine, have to be executed, which is nothing but again a sub procedure or a sub program, which was already stored somewhere in your memory location. Okay. So as and when the control enter into interrupt cycle, this particular routine have to be executed apart from your sequential mainline program. Okay. So while it is executing main program, one interrupt has been occurred, right? So whenever it receives an interrupt, then it has to execute the corresponding routine program or the set of instructions written with respect to that interrupt. Okay, so and where is this ISR in our main program? Okay, right, those address of this ISR should be made available to the CPU for execution. Okay, so that was the first steps that are done during interrupt cycle. Okay, so your program counter PC will be stored in a see, we this interrupt cycle actually it initiates with the two instructions, which is nothing but branch to a specific address. Before branching, it has to save the written address, because while executing your main program, an interrupt is caused. After servicing that interrupt, the control has to again come back to the mainline program for normal execution. Okay, so for that, an instruction is executed which is called branch and save written address. So the first step in interrupt cycle is storing the written address. It has to store somewhere in the written address. So right now your written address will be in PC program counter. Okay, so this written address which is available in PC, it has to be stored in a specific location. Okay, so where from which it can found it later when the program returns to the instruction at which it was interrupted, right? So this particular location, which is called the written address, it can be stored in a register or in a memory stack or in a specific memory location. Okay, so here for simplicity, I'm using a specific memory location, which is nothing but 0, at which I will store my written address. Okay, the address at 0, which helps for storing the written address. Now, after storing this written address, which is available in PC in the memory location, the PC will be have to be updated. It has to branch to a specific location where it has the address of your ISR. Okay, so for simplicity here, we are assuming my PC is branching to a location 1 where it has my ISR. Okay, so after pointing to your ISR, we are clearing these two bits. One is IEN and R, both are cleared. So what they are saying, what is its significance means, because no more further interrupts can occur until the previous interrupt request from the flags, neither may be FGI or FGO, that has been serviced. Okay, so it is simple that only one interrupt at a time it is serviced. Nested interrupts are not allowed, for which we are making IEN to 0. Okay, while it is doing under interrupt cycle, it has to complete the interrupt that has been occurred, it has to complete the service of that particular interrupt until unless it won't further receive any interrupt. Okay, nested interrupts are not allowed. So for which we are making IEN 0 and R0. So after this, we have an instruction address which is available in PC, which is nothing but 1. So at this particular instruction, for memory location, we have a sequential instructions to be executed by the processor. So now your processor will enter into a normal instruction cycle, right? So then it will enter into your instruction cycle and proceed for the execution of same fetch, decode, and execution. Okay, right? Because ISR is also nothing but a group of instructions to be executed by the processor, right? So it has to be executed by following it an instruction cycle only, because we have made R equal to 0. Okay, so it executes all the instructions under that ISR. Okay, and last instruction of your ISR should be written in such a way that it has to come back to your mainline program after completion of the ISR. Okay. Okay, so last instruction is nothing but branching to this particular address 0, at which you have your address of PC. Okay, it should be an indirect program address is available at 0. Okay, so those will be, this procedure is clearly explained with the help of some example. I think it is clear now the interrupt cycle, the difference between interrupt cycle and instruction cycle.
Yes, ma'am.
Okay, so is this procedure is clear? Interrupt cycle, whenever interrupt occurs, it has to service certain, it has to service or nothing but it has to execute some set of instructions which are called interrupt service routine, which is stored somewhere in the memory. So that address have to be placed into your PC. Okay, so that address we are saying 1 for simplicity right now. And after execution of this ISR, the control has to come back to the mainline program where it was interrupted. Okay, that address we call it as interrupt return address, that has to be stored first before updating with the ISR address. The return address will be updated, stored into a memory location. For simplicity, right now we are choosing a memory location, which is 0. See, this is the demonstration of interrupt cycle. See, here, this is somewhat, your main program is this. Somewhere at a PC, your program has been started. And right now, your PC at this particular, this instruction is now executing. Okay. So while executing this particular instruction, an interrupt has been generated. Okay, so either input device or output device needs service of the CPU. So that will be indicated by setting the flag bits. As and when the flag bits, either FGI or FGO are set, then it will set R to 1. Okay, so it will do only when IEN is 1. Okay, so IEN is nothing but interrupt enable flip-flop. This allows whether to generate the interrupts or whether to make the interrupts enabled or disabled. Even if devices, input or output devices are need the service of the interrupt by setting their flag bits, if the IEN bit is 0, the processor or the CPU doesn't recognize the occurrence of the interrupt because R bit will not set to 1. Okay, that was mentioned in your flowchart. So in this flowchart, IEN is considered as a master enable, interrupt enable bit. If this IEN is 0, even if these 2 bits are 1, then it won't enter into interrupt cycle because R bit will not set it to 1. Okay, so this will allows to enable or disable the interrupts. Okay, so this mask bit I can say. Okay, if this bit should be 1 for accepting any request from your peripherals, maybe input or output devices. Okay, so while your control is at this instruction, if you receive an interrupt and that too it is enabled properly, then it has to enter into interrupt cycle. Okay, so in the interrupt cycle, the return address, first step is a return address, which is nothing but 256. This has to be stored somewhere. For that, I am reserving a memory location. Okay, so the memory location 0. Here my return address is stored, which is nothing but my 256 is my return address. Okay, and your PC is loaded with the next subsequent memory location, which is PC1, at which I have my address of my program. Okay, so my IO program, it was already loaded. Okay, it was already loaded at a memory location. Let it be 1120. At this particular memory location, I have my IO program initially. So my at memory location 1, I have to write an instruction in such a way that it will jump to the ISR. Okay, so hence my instruction is like this: 0 branch unconditionally 1120. So don't confuse that this is of 16-bit. They are using octal addresses. Okay, octal addresses they are using. So each digit is 3 bits. 4 3s 12 bits only. Okay, remaining 4 bits specify the ARM code followed by I bit. Okay, and why this I is 0? Because at this particular address you have your ISR program. Okay, so ISR program is 1120 is directly available here. So hence my I bit is 0. So your control will move to this particular program. After executing this program, after executing this program, your control has to come back to main program. So it has to come back to main program. Okay. So to do so, again, one more unconditional branch instruction should be there at the end of your IO program. Okay, it branches to an address which is nothing but 0. Okay, and what it is having at 0, you don't have your main program. 0 holds the address of your main program. Okay, so the I bit is 1. It indicates that at 0 I have again one more address. At that particular location I have my main program. Okay, so this your PC branch unconditional means your PC has to be updated with 0 if this bit is 1. But your PC will not update directly with 0. It has to update by the contents of at this particular location at the contents of 0, which is nothing but 256. So your PC is updated with 256. It's nothing but the return address is happening. Returning to main program is happening. So this is how the interrupts are executed. So these are initial memory locations. Initial memory locations. You have your IO program at this particular location, and your main program is like this. After generate, this is what before interrupt. After generating the interrupt, your 0th location is loaded with the return address. Okay, and it jumps to your PC is updated with 1. This is after interrupt generation. Your PC is updated to 1. So after executing this, your control will come here and it started executing. At the end of your interrupt service routine, you have your branch unconditional instruction. So where it helps my PC to reinitialize it with 256 so that it can come back to main program. This is what interrupt cycle. Okay, so now if you combine both the things, interrupt cycle and instruction cycle, this is how your flowchart looks like. The complete computer operation flowchart. Initially, your SC, IEN and R bits are 0. And initially, we'll check the R. Right now, R is 0, so it will enter into instruction cycle. Instruction cycle start with fetch. Okay, which has 2 micro operations, transferring contents of PC to address register, because address register is only the one that is connected to the memory. Okay, so it has to first do this transfer. After that, fetch the contents at that particular memory location, which is nothing but instruction code, which is available now in IR in the next time interval T1 state. Okay, and your program counter is incremented by this time at this point itself, because to do so you don't require any bus. Okay, so this is fetch access, fetch cycle. After that, decoding is done in T2 state, and based on the T7, this recognizes whether it is register or IO or memory reference. Accordingly, the instructions are executed. Okay, this part is your instruction cycle. Okay, so at any instant of time, if any of the bit like FGI or FGO or set, then while doing execution, if either FGI or FGO are set, then the R bit is set to 1, then it will enter into interrupt cycle. So the interrupt cycle is nothing but saving the return address and changing PC to a new address where you have your ISR, and start proceeding with the same instruction cycle again, because ISR is also nothing but a set of instructions. Okay, so this is the combined computer operation which do both instruction cycle and interrupt cycle. Is there any doubts here?
No, ma'am.
So that's all for today. Instruction cycle and interrupt cycle both are important, very important questions. So please refer again. If you have any doubts, we'll see next class. Let me collect the attendance. Sixty-three absent, 67. 92, 95, 96, 100, 106, 108, 110, 130, 119, 120, 67. You are, please change your names accordingly. Who is Shruti?
100 present, ma'am.
63, 92, 95, 96, 106, 108, 110, 113, 119, 120. Okay, ma'am. Thank you. Bye.